Alright, so we're going to be starting our last and final objective in our review of chemistry unit. And it's going to be all about macromolecules. And so we're going to be looking at 4 different classes of organic compounds. And before we kind of understand exactly what a biomolecule is, we need to understand what it means by organic compounds. And so a lot of times the word organic is used to refer to living, and inorganic may refer to non-living, and that's because organic compounds are compounds that contain carbon. Normally they're bonded to an H, but this is the main element that we are concerned with. Organic compounds are carbon compounds, and the reason we usually associate them with life is because these are compounds found in living things. Even like a dead tree would still be considered organic because it contains these compounds. And so a lot of them are really, really large. They have lots and lots and lots of carbon, and they usually also have lots and lots and lots of hydrogen. And if we go back to those 4 elements that made up 96% of living things, carbon and hydrogen were both on that list. And this is the main reason why, is because these are the main molecules that make up our living cells and our living bodies. And so some examples are things like sugars, fats, the wood of the tree. All of those things are carbon-containing compounds. Now, inorganic typically does not contain carbon. I'm not going to say it never contains carbon, because over here you can see that carbon dioxide, just CO2, that gas that we exhale, it's not really considered an organic compound. It doesn't have the H's. It's not necessarily part of the living structures, and so we consider that inorganic. But for the most part, if it doesn't contain carbon, it's going to be inorganic, and this makes up a lot of your non-living materials, like just your basic oxygen gas, water. None of those contain carbon. And so which of the following is an organic compound? And so what we're looking for is carbon. Now this is actually chlorine. That's NaCl. That's sodium chloride, so no carbon there. This is calcium. No carbon there. And so the only one of those that's an organic compound, and probably a super, super, super important organic compound, that's glucose, C6H12O6. All right, so these organic compounds, we're going to talk about 4 important groups that we call macromolecules. Sometimes they're simply called biomolecules. And so macro, we've seen that before. Macro means large. And so when we say large, in terms of molecular size, they are enormous. Now they're still tiny because they're molecules, but in comparison to like a water molecule that has 3 atoms, they are going to be huge because they're going to have a much larger number of atoms. And some of them can be, thousands and hundreds of thousands of atoms together. And then the biomolecules, bio means life, so sometimes they're simply called life molecules. But we have 4 different classes that make up living matter, and we're going to spend a pretty decent amount of time on each one. We have carbohydrates, lipids, proteins, and nucleic acids. And these are kind of the basic building blocks of our bodies and of our cells. Now, each one of them is going to have a specific structure, and just a general, something to know. It's going to be seen all throughout anatomy and physiology, is that structure determines function. So as we go through the different macromolecules, we're going to look at how they're built, but we're also going to look at what they do. And so their structure is always directly related to their function. Now, 3 of the 4 are what we call a polymer. And here's another prefix to know. Poly means many. And so a polymer is a big molecule that's made up of repeats, okay? A polymer does not just apply to macromolecules. We have synthetic polymers like plastic. A spider web is actually a form of a polymer. Poly just means many, and so polymers are just made up of repeated units. If you have on a necklace that has a chain, that chain is a polymer. Each individual link is what we call a monomer, and then monomers join together to form the polymers. So when you have repeat units, those repeat units are called monomers, okay? They equal 1, mono equals 1. Many of these join together to form the polymer. So carbs, proteins, and nucleic acids are all polymers. In fact, as we go through, we're going to identify their monomers. Now, lipids are still big macromolecules. They just don't have a single repeat unit that makes them up. All right, so the 4 classes of macromolecules, we have our carbs, lipids, our proteins, and our nucleic acids. And we're about to go through each one of these one by one. This video is going to cover the first 2. We're going to take a look at carbs and we're going to take a look at lipids. All right, you do have a handout available in your packet, so you may want to have these out and handy. It's no big deal if you don't. You can always go back and do them after the fact, but this is a great study sheet in recognizing your 4 macromolecule groups, both the structures and the functions. All right, so the first one we're going to take a look at is carbohydrates. And I mentioned this in another lesson, but carbs equals sugars equals energy, okay? A lot of people are familiar with carbs because we hear it a lot in the diet world, and sometimes they get a bad rap. A lot of times people are on low-carb diets, things like that. But carbs are sugars that give us energy. They are absolutely essential. This goes back to that equation for cellular respiration. It takes place in the mitochondria of our cells, and that's where we take glucose, and in the presence of oxygen, we make energy. So we absolutely need carbohydrates in our bodies because they help us make the ATP that we need to sustain all kinds of life functions. Now, the carbs may also be structural. They can make up cell walls, and we'll take a look at that a little bit. They can also be storage, and when it says storage, they can store energy. Now, it's not a long-term energy storage, it's a short-term energy storage, and we'll take a look at that as well. And so once again, it's the main energy source. We use the sugars to make ATP. Now, in terms of structure, we can break them down into 3 groups. Here we have those lovely prefixes again. Very important, okay? We have monosaccharides, and saccharide is just a fancy name for sugar, okay? Saccharide equals sugar. So mono literally means 1 sugar. Di here means 2 sugars, and poly means many sugars. So we're going to take a look at these structures and some of the functions that they have in our bodies. So the monosaccharides are just single sugars, and so here's several examples. This one right here is probably the most notable. Glucose gets the most attention. You've probably heard about blood glucose levels, things like that. You may have seen that in relation to diabetes, if there are issues regulating blood glucose. And so monosaccharides are just single sugars, okay? They usually have 1 carbon to 2 hydrogens to 1 oxygen, like glucose is C6H12O6. And so these are your monomers. These single sugars are your monomers. And what we use them for is quick energy. Primarily that glucose molecule, that's the one that we're breaking down in cellular respiration. And these sugars help us make ATP for our cells. Now if we take 2 monosaccharides and we put them together, we get a disaccharide, okay, which means 2. And so these are going to be your double sugars. They also are going to be important for providing energy. And so we have sucrose. I don't know if you recognize that word or not, but that's basic table sugar. That's going to be like the white sugar that you may use in baking, or the white sugar that you may put in your sweet tea or Kool-Aid. We use that all the time in our kitchens. Lactose is the sugar that's in milk. You know, some people are lactose intolerant, and it's because they can't break that down very well. Maltose can be in malt beverages, but you can see that if you take 2 monosaccharides, once again, those are the monomers, and you put them together, then you make a disaccharide. And then we have our polysaccharides, and poly means many, so literally many sugars, and it says many, many simple sugars. We're not just talking 3 or 4 or 5. A lot of them have long chains or long branches of those sugars. And so these are the ones that are going to play a role in energy storage. They can help store energy short term for our bodies, and they can also be structural. They can make up cell walls. And so the monosaccharides were the monomer. The polysaccharides are going to be the polymers for our carbohydrates. As you can see, there are many units joined together, and we can see those repeats. So we're going to take a look at some important ones. These are 4 important ones. We're going to take a look at 3 of them in more detail, but these are some polysaccharides to know. Starch. This is a word that you may have heard. You may have used it in your kitchen as well, maybe corn starch or something like that. But this is a polysaccharide that is going to store energy in plants. And so I love me some starchy, vegetables or grains like potatoes and pastas, rice. Some of your fruits are starchy like corn. So starches are just big chains of sugars. And you can see here some basic structures of what starch might look like. Lots and lots and lots of monosaccharides. And so starch is sugar storage for plants. So when you eat like potatoes and things like that, you're eating the starch and then your body breaks them down to get those simple sugars. Glycogen is how we store energy in us. So this is energy storage in animals. And so a lot of this happens in our liver. And so if you have excess glucose, you may store it in the form of glycogen. And then when you need energy, glycogen can be broken down to release that energy. And so this is stored in our liver. It's also stored in our muscle cells. And then cellulose, this is one of those structural ones. Cellulose is a big polysaccharide. Here's the structure here. It's a big polysaccharide that's in plant cell walls. And this is what we call fiber in our diet. It's not digestible. We don't have the enzymes to break it down. And so a lot of times if you're having trouble going to the bathroom, you will eat fiber, and that will, things like bran and some of your stalky vegetables. And when you eat fiber, it kind of helps push that material through your digestive system to help you go to the bathroom. But cellulose is kind of these long, think about celery, those long stringy things in celery, and that kind of always makes me think of cellulose because that's essentially what those things are. Now there's some couple others that you don't really have to know, but chitin is another one that makes up cell walls like in mushrooms and fungi and like exoskeletons of insects. And then peptidoglycan is something that you'll find in bacteria. But these are going to be your big polysaccharides that you need to know. And so we've got some sugar storage in plants and animals, and we have the structure of plant cell walls. All right, so you do have this. This can help you fill in your table if you want to do that. And then we're also going to talk about lipids in this video. And lipids were the only group that are not polymers. Now, they are still big macromolecules, but they don't have a repeat that repeats itself over and over and over again. So we just simply say that they're non-polymers. Now, what makes a lipid is that they're hydrophobic. And hydro means water, and phobia refers to fear. And so these guys are water-fearing, okay? They will not dissolve in water. They will repel water. And these are going to be your fats, oils, waxes, steroids, and phospholipids. So we're going to look at 3 main types. We're going to look at triglycerides, phospholipids, and steroids. And the one thing that they all have in common is they're all hydrophobic, okay? Now, your triglycerides are your fats and oils. And once again, I know there's a lot of people that talk about fats and oils and diets and things like that, saturated, non-saturated. We're going to look at that here in a minute. But we do need fat in our body because fats can store energy long term. So where those sugars, like starch and glycogen, could store energy short term, fats can store energy long term. They can actually store a lot more energy than those carbs. And so the basic structure of a triglyceride is it has a backbone called a glycerol molecule. That's this part right here. And then the prefix tri comes from the fact that there are 3 fatty acid tails. And as you can see in the picture here, this is the molecular structure. There's lots of carbons and lots of hydrogens, okay? These tails are literally long hydrocarbon chains. And these are the part of the molecule that do not like water. They're nonpolar. And so they are going to repel and turn away from water. They will not be good friends with the water molecules. And so it's these fatty acids that can be saturated or unsaturated. But your triglycerides are always this glycerol with 3 fatty acid tails. Now the saturated and unsaturated has to do with double bonds. So in those long tails, each of these lines represents a bond, and carbon always forms 4 bonds. If you have a double bond, it means you don't have as many hydrogens that are necessary. And so you see how this one, the hydrogens are going all the way around. We say that that one is saturated because it's saturated with hydrogens around there. And these are the ones that are going to be solid at room temp. Your saturated fats are solid at room temp, and saturated fats are your animal fats. So these are the ones that you're going to find in our bodies. Things like bacon grease or lard, all of those are saturated fats. And these are the ones that could lead to some heart disease and stroke. They can build up in your vessels. And so while we need fat, we don't want to have excess, especially fats that aren't very good for us, even if they taste yummy. And so unsaturated fatty acids, once that double bond is there, you can see that there's some hydrogens missing. And so what happens is it causes these chains to kink a little bit. And so they can't kind of form as close together. And so it kind of gives them a little bit more of a fluidity. And so these are the ones that are liquid at room temp, and these are going to be your plant oils. And these are the ones that are healthier for you to eat. Things like olive oil, avocado oils. They can have some health benefits, improving cholesterol. So these are going to be your healthier fats. But both of them have, these fatty acids are the ones that you'll find in your triglycerides. So in plants, you'll find these unsaturated fatty acids, and in animals, you'll find these saturated fatty acids. Now, something you may hear in the diet world and health world are these trans fats, or something called hydrogenated oils. What they can do is they can kind of blast these liquid oils with hydrogen, and it makes them more solid. But those can be unhealthy for you. They can increase your bad cholesterol and lower your good cholesterol. So really trans fats aren't very good for you. Once again, even though they may taste good, we use them in a lot of the foods that you can find, a lot of processed foods especially, but they're really not very healthy for us. Now another structure of lipids are phospholipids, and these contain a phosphate, which is where that comes from. They still contain the glycerol, and then they have fatty acids. So once again, they have a region that does not like water. But what's interesting about the phospholipids is they are amphipathic, okay? Now, ampha refers to kind of 2 states. And so we are going to have a hydrophilic region, and so that's going to be the head of the phospholipids. So over here you can see that phosphate group, and then my glycerol backbone, okay? So this particular portion of the phospholipid is hydrophilic, which means it likes water. It's polar, and it's going to not repel water. But these fatty acid tails, these long hydrocarbon chains, they do not like water. They are hydrophobic. And so that's what amphipathic means. One part of it likes water, one part of it doesn't. And these guys are super important because they make up our cell membranes. They form what's called a bilayer. And that has to do with the water-loving, water-fearing different portions of the phospholipid. And then the last one that we're going to talk about are steroids. Most people have heard of these, and we're not necessarily talking about like the illegal steroids. We're talking about just the natural steroids that you find in your body. They are a little bit different. They don't have those long fatty acid tails. They have a 4-ring structure. But what they do have in common is they are still hydrophobic. Steroids and water do not mix. These guys are going to be nonpolar, and they are not going to dissolve in water. So you can find steroids in the cell membrane, and that's cholesterol. It helps to kind of stabilize the membrane and change the freezing temp. And then some of them act as hormones. They could also be things like vitamin D that help us in calcium homeostasis. I think most people have probably heard of these. These are some of your sex hormones, estrogen in females, testosterone. These are going to give secondary sex characteristics at puberty. Estrogen acts on the ovaries, testosterone acts on the testes. And so all of these are hydrophobic molecules, but they do have a little bit different of a structure than some of the other lipids that we looked at. And that is going to take us to the end of this video. So here's your lipid summary. You may want to fill that in on your diagram. I would encourage you to kind of summarize it all in your charts. And then the next video, we are going to cover the last two of our macromolecules.